Physics Part 217. You should be able to recognize the use of equation A is equal to minus w square into x as the defining equation of simple harmonic motion. You should be able to recall and use x is equal to x theta, x sine wt as a solution to the equation A is equal to minus w square into x. You should be able to recognize and use v is equal to v0 cos wt and v is equal to plus minus w into under root x0 square minus x square. You should be able to describe with graphical examples the changes in the displacement velocity, the changes in the displacement, the changes in velocity, and the changes in acceleration during simple harmonic motion. Describe simple examples of free oscillations. Some movements involve repetitive to and fro motion, such as pendulum and beating of a heart, the motion of a child on a swing, and the vibrations of the guitar string. Another example would be a mass bouncing up and down on a spring as illustrated in the figure. One complete movement from the starting or rest point up, then down, finally back up to the rest position is known as oscillation. The time taken for one complete oscillation is referred to as the period t of the oscillation. The oscillations repeat themselves. The number of oscillations per unit time is frequency f. Frequency may be measured in hertz, where 1 hertz is 1 oscillation per second. 1 hertz is equal to 1 second. However, frequency may also be measured in minutes, hours, etc. For example, it would be appropriate to measure the frequency of the tides in hours. Since period t is the time of one oscillation, then frequency f is equal to 1 over t. As the mass oscillates, it moves from its rest position. This distance from the equilibrium position is known as the displacement. This is a vector quantity since the displacement may be on either side of the equilibrium position. The amplitude is a scalar quantity and is the maximum displacement. Some oscillations maintain a constant period even when the amplitude of the oscillation changes. Galileo discovered this fact for a pendulum. He timed the swings of an oil lamp in Pisa Cathedral using his pulse as a measure of time. Oscillators that have a constant time period are called isochronous and may be made use of the timing device. For example, in quartz watches, the oscillations of a small quartz crystal provide constant time intervals. Galileo's experiment was not precise, and we now know that a pendulum swinging with a large amplitude is not isochronous. The quantities period, frequency, displacement, and amplitude should be familiar from our study of the waves in Chapter 8. It should not be a surprise to meet them again, as the idea of oscillations is vital to the understanding of the waves. Displacement time graphs. It is possible to plot a displacement time graph, as we can see it in the chapter. For oscillators, one experimental method is illustrated in the figure. A mass on a spring oscillates above position sensor that is connected to a computer through a data logging interface, causing a trace to appear on the monitor. The graph describing the vibration of the displacement with time may have different shapes depending on the oscillating system. I'll tell you more about the same in my next video.